Hello everyone, it's David here. At the start of today's lesson I'm going to be telling you something about the beauty of phi, a number which I talked about yesterday in the hall. Well, yesterday we saw this rectangle which we experimented with and tried to make as beautiful as possible. And in doing so, we've introduced this number phi right here. The symbol for phi is here, and phi is approximately this number. It's also known as the golden ratio. And in the context of the rectangle we looked at, it was the ratio of this length, this length, divided by this length. You can see that approximately we managed to make the ratio, coinciding with the golden spiral. Well, today we're looking at phi in a whole range of different contexts, and here's the first one. All the Italian students will know this. What we have here is a famous sequence known as the Fibonacci sequence. And if you look at it closely, you can see it has a rule. You could write it down like this. Each term is the sum of the two preceding, and so on. What's this got to do with phi? Well, when we put these numbers in a spreadsheet and calculate the ratio between each term of the sequence, we find at the beginning 1, because 1 divided by 1 is 1, and then 2, because 2 divided by 1 is 2, and then 1.5, because 3 divided by 2 is 1.5, and so on. And when we graph those numbers, we see, as if by magic, this number phi appears. And then the natural question is, what happens if we change the numbers from 1 and 1? Because they're not very interesting. Let's try 4. You can see again that the number phi appears. What's that I hear you say? Let's try a negative number? Okay, let's try negative 3. The number phi appears again. Still not convinced? Let's try 0.8. It happens again. Not good enough for you? Okay, let's try pi at the beginning. And again, the golden ratio appears again. Now this is just one place where this number pops up unexpectedly. And of course, we could try to prove that that always happens. So I'll leave this as an exercise for you to read. It's a proof that in any Fibonacci sequence, if you have the ratio of two terms reaching a limit, then that limit must be the golden ratio. When we take this equality and rearrange it to get a quadratic right here, and then when we use our knowledge of maths to solve the quadratic using the quadratic formula, which you can all do, you've all done it, we end up with the conclusion down here. When we solve for un, that the ratio between each term of the Fibonacci sequence gets closer and closer to the golden ratio. Okay, I'll hand you over to your TOK teacher now. You're going to look at a whole range of different contexts where this number appears, and I hope you find it interesting. Oh, by the way, I've made this video with my interactive whiteboard, and as many of you know, I'm trying to get a CAS activity up and running where you can make lots of videos that are even more interesting than the one you've just seen. So get in touch with me if you're interested in doing that.